Hi, my name is Nikola Marinčić. Welcome to the second iteration of the class An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are currently in the week 2. And before we continue with the new things that I was planned to tell you, maybe let's review some concepts that we talked before. We made an experiment introducing kind of a device which could precisely measure our position in space at any point in time, and we deduced that it probably would be some kind of a curve which would record our movement of 300 meters in 20 seconds. Then we said, okay, this curve gives us a lot of information. The curvature itself gives us much more information than a linear model. So we said, okay, what can we deduce? Then we started subdividing these time intervals. We subdivided them into 4 intervals first, and we got 4 values of the average speed. In the next iteration, we subdivided it into 50 intervals and got 50 values for the average speed. And then on the bottom right, you can see a curve which shows the average speed over time. And you can imagine that the more we increase the resolution of subdivision of time, that this blue jagged line becomes more and more like a curve. And the question here really is how far we can continue to subdivide and what will be the limit of this operation. And then we came to a very important question of derivatives, and this is, considering that our time interval cannot be 0, what would be the best possible approximation of the speed around the moment in time t? Why it cannot be 0? Because if we divide any kind of magnitude by 0, this is simply not defined in mathematics. So if this interval cannot be 0, what then would be the best possible approximation of speed around the moment in time t? On this image, we introduced the variable t to store our current moment in time, and we introduced an infinitesimal dt, which is a kind of virtual quantity which is larger than 0 but smaller than any feasible measurement. By adding dt to t, we get a new point in time, which is t plus dt, and we get a new point in distance, which is s of t plus dt. This is not yet a correct formula, because the idea of this derivative is that it's a kind of a dynamic variable that moves towards a certain value. So as it moves towards a certain value, the ratio between the green and the purple approaches some value as dt approaches 0. So to turn this formula into a correct formula, we need to say that dt approaches 0. And in 1821, Cauchy introduced the idea of a limit which was able to formalize this idea so that we do not have to use language to say as dt approaches 0 in order to formally speak about derivatives. Also, limit notation allows us not to use the special variable dt, but we can use any variable such as h, and then the limit operator turns it into this shrinking variable. Then we talked about chaining functions. We had individual functions, and each of them has an input as an output. But then we can change an output of one function and take it as an input of the next one. At the end, we have an output which is modulated through this chain. So all the functions in this chain, for example, f, g, h, and k, are modulating our output. How does this look like is animated here. So as you can see, for each change of input, the output changes, but you can see that the steps before also influence what is going to happen in the output. The question is, what happens when we add the infinitesimal in this story? So when I add infinitesimal to the input, which is this orange length, we get some more infinitesimals which are propagated through the whole chain, ending with the output, which also has its own output infinitesimal, which we name d output. What is then the derivative of this chain? And in the last class, I explained that it is simply the ratio between the d output over the d input. So the ratio between two fictitious magnitudes. What we also introduced last time is the chain rule, which is a rule of calculus which allows us to decompose this output to input ratio. So sometimes this chain of functions is quite complicated, therefore the calculation of the derivative would be very complicated as well. But what we can do is we can decompose this ratio to a number of simpler expressions that we can multiply together. We can say that d output over d input is equal to the d output over dh times dh over dg times dg over df times df over d input. Now we have 4 derivatives instead of 1, and these 4 might be much easier to compute than the one which is very complex and long. We can still get from this long expression to our original expression by simply cancelling the values, cancelling dh's, dg's, df's. What derivative tells us about functions? For example, we had a function sine of x squared, and we computed this derivative to be cosine of x squared times 2x. Now we can ask, what is the relation between these two functions? At the points where the green line has its maxima, the blue line is crossing the coordinate axis and it equals 0. It is the same with minima. For all the minimal values of the green line, blue line is simply equal to 0. Therefore, derivatives indicate some kind of extreme values of a function. Today's topic, we will start by introducing the application of derivatives. And the first thing will be how to maximize or minimize function's output. And the function that we will try to minimize or maximize is z equals to sine of x squared. And we have its derivative, which shows us at which points this function might have maxima or minima. And in these points, the blue line is equal to 0, so crosses the horizontal axis. What we can do to minimize or maximize a function, inquire when does this derivative equal to 0. For example, when is dz over dx equal to 0? And since dz over dx is cosine of x squared times 2x, we can simply ask when is this expression equal to 0. If we can solve this equation with one unknown x, then we will get the points of minima and maxima. But for a long chain of nested expressions, it might be very difficult actually to solve such an equation, or maybe even impossible. So there needs to be a better way to do this thing. To introduce this better way, we will look at another perspective of the derivatives.
So what is this new perspective to derivatives about? Here we will try to figure it out from the perspective of a 2D graph. So we have two axes, x and y, and the coordinate origin 0, 0. When we introduce a function, we are somehow starting to couple x and y dimension. So if this is a curve, and if this curve represents a function, then we can name this function, for example, f of x, and now y would be f of x, which means that y is functionally dependent on x. What does that mean? So let's evaluate this function at a single point. Let's choose, for example, this point here. What is an input and what is an output here? So to find an input, we need to project this point on the x-axis. When we do this, the trace of this projection, we can call this, for example, x. And what is x actually equal to? X is actually equal to this distance here. So this is the input. Yeah? And then what is the output? Well, to get the output, we need to project the same point on the other axis, y. So now this point here would be, for example, y, which is f of x. So this length here is then called an output. And it is an output for the input x. So this is output of x. Okay, now the next thing we did is we introduced another point, for example here. And now we can project this point to both axes. And we also said that this distance between these 2 points, we will call it dx. Why? Because in principle, we want to make this value as small as possible, but let's assume that we start somewhere, so as some kind of concrete value, which will then try to approach x. Okay, if this point is x, then this point here, its x projection is x plus dx, and its y projection is f of x plus dx. As you can see, the function between these 2 points, this one here and this one here, is a curve, so it's a curved red line. So f of x is not a straight line, it's kind of non-linear. But if we make a line through these 2 points, what do we get? This line is now called a secant line. It's a secant line. It means that it's crossing this curve f of x, at 2 points. And now the question to this new perspective is, what happens then when we start shrinking dx? So, for example, if we put this point here, our secant line would be a little bit different. Okay, and then what happens when you start making it even closer to x? Let's go a bit further. If we make the point x plus dx here, then we get this line. If we make it here, then we get this line. The question is, what happens as dx approaches 0? What is this secant line approaching? Answering this question introduces a new perspective towards derivatives.
So what happens in this case is that as dt approaches 0, the secant line connecting 2 points, it approaches the tangent line at a single point t. This property of derivatives is very useful to find the minima or maxima of any function. So let's look at one more example. What is the relation of the original function z equals sine of x squared and its derivative? So derivative gives us slope at any point of time x. So as we move x towards the left now, we can see that at each point in which the vertical axis is touching our curve, we can project a new line whose slope is equal to the derivative at that point. Let's see what kind of slopes indicate what kind of derivative values. For example, if you have a positive derivative value, we have a positive slope, and this is slope which looks something like this. If we have zero derivative value, we have a zero slope, therefore it's just a horizontal line. It has no slope. Slope is equal to 0. If the derivative is a negative value, then the slope will be negative, as indicated on this example. Okay, but how we can use this information here to actually gradually maximize or minimize function's output? Let's look at this example here. We have a function, which is indicated by the green line. We have a tangent at the point x, and the slope of the red line is equal to the derivative at the point of time x. We need to ask a couple of questions here. So first of them is, in which direction do we need actually to move x to maximize the output? So should we move it to the left or to the right? If we move it to the left, then the output of the function would be smaller than for the input x. Therefore, we should move it to the right. Yeah, so we need to increase x. Okay, the next question is, according to the last slide, what kind of derivative value is this? Is it positive value? Is it negative value? Or is it equal to 0? If you look at the last slide, you will realize that this kind of slope indicates a positive derivative value. And then the last question would be, is it better to increase x by a small value, like this? Or maybe we should use a larger value. If we take a large value to increase x, we might end up in a point in which we would actually minimize the function, not maximize it. So it is a much better idea to move x by a small value, because this will, in most of the cases, guarantee us that we will actually end up maximizing the function and not minimizing it, if that's what we want to do. Okay, so how do we express this mathematically? So how can we actually maximize function's output? We can do it by adding the derivative value of the function at this point of time x to the input, but not just adding it. Before adding it, we need to multiply the derivative by a small number c. So this will help us to actually move with a small step towards right. And this is how the function looks like. So we had an old point. Our point x is actually x old, and we need to know the x new, which will be a value of x, which will maximize our function. So we can see that the x new is equal to the x old plus the derivative of the function at the point x multiplied by c, which is some kind of small number, for example 0.01. Let's see if this works in this case when the x is actually on the other side of the maximum. So now, in order to maximize the function, we actually need to go left. If we ask what is the derivative value here, is it positive or negative? From the last slide, you can deduce that this is actually a negative derivative value. And again, we will use very small steps to maximize our function. So if you see what happens now, you can ask, is this formula still valid? And actually you will realize that it is working, because to get the x new, we take the x old and we add the value of the derivative. But since the value of the derivative is now a negative number, this simply means that we will be actually subtracting from the x old, which means that we will go to the left. And by going to the left, we will actually maximize the output of our function y. So this formula really works. Now, a very similar question: how do we actually minimize the function's output? Well, we can introduce kind of analogous thinking to the last case and simply ask the same questions again. So, if we want to minimize it, should we go left or right? We should go left. So x needs to decrease. On the right side, x actually needs to increase, needs to move to the right. Okay, on the left side, what kind of derivative value do we have? We have a positive derivative value. What kind of derivative value we have on the right? We have, again, negative derivative value. Should we move by a small step towards the left and towards the right? Yes, it's much better to do it than the large step, because we might actually end up maximizing the function instead of minimizing it. And the only thing which really changes if we want to implement this is that we now need to subtract the derivative value from the input. Again, derivative multiplied by a small number c. So now the formula is very similar, except it has a different sign within the expression. To get the x new, we have to take the x old and subtract the value of the derivative multiplied by some small number c. And now let's see an example. We will now try to actually gradually minimize and maximize a function, and we will use the same function that we already used before, which is sine of x squared, and we know already its derivative. It is cosine of x squared times 2x.
To learn how to gradually minimize or maximize functions, I've created a couple of exercises that you can find on my GitHub page, Machine Intelligence. They are here, exercise 1, 2, and 3. And we will first start with the exercise 1. If you would like to exercise, you have multiple choices. You can either install Anaconda package. I'm sure you can find many guides on Google how to do exactly that. Or you can use Google Colab like we did before. So I will show once again how we can do that. So I will go to Google and type COLAB to find it. And it is the first link on my list. Now, when I'm in Colab, I will click on GitHub to import my GitHub repository. So what I need to do is go to my GitHub repository, Machine Intelligence. I copy this link here and paste it here. Press enter, and then Google will recreate the content of my repository. And if I click on exercise 1, Google will open it in Colab. So right now, the exercise says create a Python function that implements z of x equals sine of x squared, and you can type the code here. But I'm personally more comfortable to use my own local installation, so I will show these exercises by using my own local installation of Anaconda. The first exercise is about minimizing and maximizing a single variable functions. So let's do some of these exercises. The first task is to create a Python function that implements z of x equals sine of x squared. So there is a sine function here, but if I say sine of 5, you will see that name sine is not defined. So Python by default does not know about sine function. We need to import it, and there are multiple ways to do it. We can import it from the math package, or we can import it from the NumPy package, which is a library for numerical computing. And I will use NumPy's implementation of trigonometric functions. So to import NumPy, I will say import NumPy as np. Now this np is a placeholder. If we put it before the function, and if the function is defined in it, this is how we can run it. So instead of saying sine of 5, we can say np.sine of 5. Let's now do what we are asked to do. Let's implement the function z of x equals sine of x squared. So I will type def to define a function. It will be z, and the input of this function will be x, and I will return np.sine of x times x. Okay. Now the task is to evaluate the function z of x for different values of x. And now we have this graph here, so we can make sure that it's kind of working, let's try to see what is the value of this function for the input 1. So z of 1. Z of 1 is 0.84, and if we look at it here, it's kind of, yeah, close to 1, but not 1, so this seems fine. Let's try it for the value of 4. Z of 4 equals negative 0.28. Okay, this makes sense. If we are at the point 4 and go down, it's around negative 0.3. All right. Now it says, create a Python function which implements the derivative function cosine of x squared times 2x. So this is the derivative function to our original function z of x. But do not forget that this is simply a function, so nothing special about it. It's just a function like any other. So we can type def dz, let's call it dz underscore dx. And the input is x again. And what this function will return, it will return np.cosine of x times 2 times x. So x squared times 2x. I'm making it simple intentionally. All right, now it says evaluate this function for different values of x. And let's see. So as you can see, this function is not restricted between 1 and negative 1 like the previous one. This one starts expanding the further away we go from the origin. So let's see. dz over dx of 1 should be a little bit over 1. And let's see what it is at the value 3. It should be negative, yeah, it is negative 5.46. All right. Now, the task is to introduce a variable xold that stores numbers and pass these values to both functions. So the idea here is not to pass a concrete number here, like 3 or 2 or whatever, but to pass whatever we store in a variable to these functions. So we make a variable called xold, and let's put some value in it, for example, 5. And now it says pass these values, actually should be pass this value to both functions. So we can say our first function is z, and the next function is zx over dx. So z of xold, this gives us negative 0.13, and dz over dx of xold, this will give us 9.91. And now we have a more concrete example. So now we have this function, and we are at the point xold equals 1.5. This point is marked on the graph, it is here, and it has a positive value for the function z and a negative value for the derivative function. And the task is to minimize our function z of x, so the green line. We need to write code that computes the new value of x, which is x new, which if taken as an input to z of x will decrease it. So somehow we need to decrease this output. Okay, what do? We say xold is equal to 1.5. All right, as we have introduced on the slides, x new is simply xold, and now since we want to decrease it, we will use the sign minus the derivative at that point, which is dz over dx at the point xold times some small number. Let's make this number 0.01, for example. All right, now let's see what is the value of x new. So the value of x new is 1.5188. So this is higher than 1.5. It means that we moved to the right on this graph. And if we evaluate what is then the value of this function for this new point x new, we can do z of x new, and we get that the value is 0.741. And let's see what is the value of the xold for the same function. The value was 0.778. So definitely the value at the new point is lower than the value in the old point. So we succeeded to minimize this function. And now the question is, should we move x to the left or to the right of the graph? So an easy way to evaluate this is to simply say x new, which is the new point that we got, minus xold. So if this value is positive, it means we move to the right. If this value is negative, this means we move to the left. And as we already determined, this value is positive, so we moved for a tiny amount to the right. The next exercise asks us that we are at the point x old is negative 0.5. So if we are here and we wish to maximize our function, so we want this green line to become larger by moving left or right, write code that computes the new value of x new, which if taken as an input to z of x will increase it. All right, let's do that. So x old equals negative 0.5 and x new should be x old. We want to maximize it, so the sign will be plus dz over dx of x old times some small number, 0.01. All right, let's now see what is the value of x new. It is negative 0.509, which is smaller than x old. Let's now see if we succeeded in maximizing our function. So I will evaluate the function z at the point x old. The value used to be 0.24, 0.247, so this is the length of 0.247. And now let's see what is z of x new. And the z of x new is larger, it is 0.256. So again, should we move x to the left or to the right, we can simply say x new minus x old. We get it's a negative number, which means that we moved to the left here. And that's it for the first exercise.
We will try to minimize and maximize one more function, and this function is actually very much used in machine learning. It has very big historical significance in the history of machine learning, and it's called a logistic or sigmoid function. And its formula is 1 over 1 plus e to the power of negative t. This formula is not really complicated. What it does is actually squishes any input that we give to it, for example, negative 100 or plus 100, into a very small range, which is from 0 to 1. As you can see, the value of the function for x equals 0 is 0.5, and as we go further towards the right, the output of the function starts approaching 1. And if on the other side we go to the left, for a very small negative value, the output of this function will approach 0. If you're really interested, by all means, do not hesitate to try to actually derive what is the derivative of this function, but I will not do this during this class. So I will just tell you the derivative of the sigmoid function is the output of this function times 1 minus the output of this function. Therefore, this function has a very, very simple derivative to compute.
Second exercise is about minimizing or maximizing the sigmoid function. But first, we need to implement the sigmoid function. Again, this function uses some mathematical notation which is not in the standard Python library, so we need to import it. And what is not there, it is this function e to the negative x, which is an exponential function. So again, if we want to use mathematical functions, we can import them from the math module, or we can import them from the NumPy. This is a library for numerical computation. So I will say import NumPy as MP. And now if I want an exponential function, I can say MP exponential of, for example, 1, and I get the value of e to the 1. Okay, our first task is to implement the sigmoid function in Python. So I will call it def sigmoid, and the input to this function will be x. Now simply I need to interpret this formula here in Python. So what will this function return? It will return 1 divided by, I will put it in parentheses, 1 plus numpy, that exponential function of negative x. Let's see if it is working. We can see it by doing the next task, which is evaluate the sigmoid function for various values of x and explain its properties. All right, let's first evaluate it for the x equals 0, because we know that this function returns 0.5 for the input 0, sigmoid of 0, and we get 0.5, as we thought we will. So now let's try some other numbers. If I say input is equal to 4, then this function will be kind of close to 1. If I say negative 4, this function should be close to 0. So the larger number I take, for example 100, the closer to 1 we get. So this is not really 1, but computer has a limited space to store decimal values, so it kind of rounds them at one moment. So if we say negative 100, it will say it's a very, very small number, 0.00044 times 372. Now the next task is to implement the function that returns the derivative of the sigmoid function. And we have here the derivative, which is just the output of the sigmoid function times 1 minus the output of sigmoid function. And in the blue line we can see the graph of the sigmoid derivative function. Okay, let's do it. DEF sigmoid derivative, the input x, and I will return sigmoid of x. So now in this return statement I'm using the function that did not exist before, but I defined it as a sigmoid function. So since I defined this function sigmoid before, now I can use it in any other function, so I can have nested functions. So I will return sigmoid x times 1 minus sigmoid x. It says evaluate the sigmoid derivative function for various values of x and explain its properties. All right, let's again do it for the input x equals 0. So sigmoid derivative of 0, and we get 0.25. So the interesting thing about the sigmoid function is that its maximal value is here when for the input x equals 0, and it's only 0.25. When we move to the left or to the right, this function should output smaller and smaller values. So if we say derivative of 3, it will be kind of close to 0. And because this function is symmetrical over the y-axis, the derivative of this function at the point x equals 3 should be the same as the derivative of this function for the point x equals negative 3. So it has the same value. And now let's do this one exercise that we have. It says if we are at the point x old equals 2 and wish to minimize our function sigmoid of x, write code that computes the new value of x, x new, which if taken as an input to sigmoid of x will decrease it. So the old value of x is 2. All right, and we need to define x new that will be the input value which will minimize our function. So x new equals x old, because we want to minimize it, we'll use the negative sign, minus the derivative of the sigmoid function, which is sigmoid derivative of x old times a small number. Okay, and now let's see what x new is equal to. So x new is 1.989, which is smaller than 2. So we successfully minimized our function. Let's now compute the output of the sigmoid function for these two inputs, x old and x new. So sigmoid of x old is 0.8807, and the sigmoid of x new is 0.879, which is smaller than the output of the sigmoid function for the point x old, which means that we successfully minimized it. Now it says calculate the difference between the output of the x new and x old. And what does this actually mean? X new minus x old. This just tells us that if this value is negative, like it is now, it tells us that to minimize the function, we need to move to the left. So this is kind of logical, since this is the input 2, and in order to minimize this function, we need to go to the left so that this value of the output is smaller. And then another exercise, it says we are at the point x old equals negative 4, and we wish to maximize our function sigmoid of x. Okay, we'll do the same thing. We'll say x new equals x old, and we now want to maximize our function, so we'll say plus sigmoid derivative of x old times some small number. All right, let's now see what is the value of x new. It is negative 3.998. So this is larger than negative 4. Negative 4 is here, and this value is on the right. So it looks like we are actually maximizing this function. Now it says calculate the difference between the output of the x new and x old. Again, this can be used to determine whether we are moving to the left or to the right. So x new minus x old is 0.017, which means we have moved a tiny amount towards the right. And that's it for this exercise.
The next topic we will be talking about is gradient. Okay, but before I tell you what the gradient is, let's first investigate what kind of functions have we been working with all this time. If you see these two functions, x squared and sine of x, and if we investigate the relation of the input and the output, we'll see that these functions actually have one input, and they assign this one input to a single output y. Yeah? So the input is x and the output is y in both cases. But this is not the only kind of function that we can create. A function, for example, can have multiple inputs. Let's look at this function, for example. It's a function f is equal to f of x and y. So it has two inputs, x and y, and its output is x times y. So the output of the function is the same as multiplying these two inputs together. So this is a so-called multivariable function. Yeah, function with two inputs. But the number of inputs, this is not something which is restricted. We can have 1 million inputs in our function, and still it needs to have one output to be a function. A multivariable function maps multiple inputs to a single output. So single variable functions and their derivatives and the calculus of single variable functions is something that we usually learn at school. Maybe not all of you will have learned this in school, but most of you probably had done it, although I do not expect you to remember it. However, multivariable functions and their derivatives, and the term gradient as well, they are not something that we would study at, for example, architecture school or at some kind of non-strictly engineering university or faculty. They belong to kind of higher mathematical education, which we will have if you were an engineer or mathematician. And then there is a very peculiar interpretation of multivariable functions which has to do with space.
If you look at functions of a single variable, such as this f of x, which associates an input x to an output y, then the question is how we can visualize this relationship between x and y. One way to do it is by combining two number lines. So the input has its own number line, and then each point in this input is associated to a single output, and this output can be represented on a second number line. So if you take one number line, for example x-axis, and then take another number line, for example y-axis, and put them orthogonal to each other, you create a plane. What is this plane about? Well, this plane shows you the relationship between x and y. So for example, if you have a number of points here in this plane, then to each point on this plane corresponds a pair of coordinates. For example, in this case, x1, y1, x2, y2, x3, y3, and so on. What is a function then? Function is not about relating just a few points. Function in principle correlates all the possible points in this plane, which are associated with one another. Let's say that this is now f of x. Or this would be another function which relates x and y. How about this one? This is not a function, because if we take an x here, for example, x4, and make a vertical line, you will see that for the input f4, there are now two outputs. If an input has two outputs, then this is definitely not a function, so this kind of things we must discard. The question is, what happens when a function has two inputs? For example, if we have a function g, which takes inputs x and y, and here again we have x and y-axis. What is now going on? Well, now the meaning of these points here is somewhat different. They are no longer showing the relationships between x and y, but they are the data. They are the inputs of this function g, which then maps them to some output. If these are inputs, x1, y1, x2, y2, if these points are valid inputs, and they are valid inputs, where does the output live? Well, one thing to realize is the output cannot live in this same space. The output needs to somehow be outside. So what we can do is, again, we can play this game with number lines, and we can say, if I would draw this in 3D, if this is x and this is y, and they're of course orthogonal in the same way as these two axes are orthogonal, then we can create a third axis, which we can call z, which will be orthogonal to both of these axes, or orthogonal to this plane, and then each point in this plane, x and y, will be associated with some point which lives on the z-axis. So then if these are inputs, this would be the output of that function. And then we would say z equals g of x and y. Let's see this in more detail. What we have here is called GeoGebra 3D calculator, and we can use it to visualize in 3D functions which have two inputs. So first of all, let's create a point on the plane, on the xy plane, which is bounded by the green and the red line. So I will create one slider called x, and this slider can take values from -5 to 5, and I will create another slider called y with the same domain. Now I will create a point in space here, and it's going to be a three-dimensional point, but I will restrict the z-coordinate to be 0. So if I double click, I can say that the first coordinate is x, the second coordinate is y, and the third coordinate is 0. So what happens now, here's the point, is when I move the x slider, the point moves in the x direction. This can be visualized. And when I move it in the y direction, you will see the movement across the green axis. Now let's try to visualize a function of two variables, for example, small x and small y, which will multiply them, so x times y. As you can see, this is some kind of three-dimensional shape. So whatever happens in the red and green plane somehow has the output in the blue direction. So the question is, if we now wanted to put this point A on top of this plane, how we would do it? So I can double click this point and say that on the z-axis, instead of having it 0, we can have it A of this x and y's. And now this point is on the plane. We can still move it in x and y directions because these are our input parameters. And for all of these input parameters, you will see that this point is actually moving on the z direction. And how is it moving? It is very simple to predict. For example, if x is equal to 1 and y is equal to 1, then the height of this point will be 1. If x is equal to 2, the height of this point will be at 2. So in this sense, we can think about functions as some kind of manifestations in space. For example, if we have a two-input function, we can think about it as a certain plane in a three-dimensional space. This is a very interesting perspective to functions. However, this kind of breaks down in machine learning, and I do not encourage you to think in this way and to think about derivatives on this kind of geometrical three-dimensional schemas. I think this is not very helpful. Why? Because in machine learning, we deal with a very, very large number of input. So our input space will not have two inputs, it will have maybe 1 or 15 million inputs. So simply understand that visualizing these things is not of primary importance, and it will actually restrict you to think about what the derivative is doing in this case. So in my perspective, it's much better to think about inputs living on a certain number line, continuous number line, and then each of the inputs having its own number line separately.
Let's look at this function. This is the function which has two inputs, x and y, and it multiplies them, resulting with the output f. Let's now ask what happens if we restrict our input x to be 0. For example, then this will be a function of 0 and y, which will then multiply 0 and y. And as you know, multiplying anything by 0 will result with 0. Let's look at another example. Now, let's investigate what happens when the x is equal to 2 and y is equal to 3. X moves upwards to 2 and y as well moves upwards to 3. Therefore, our output is 6. But now, our number lines perspective allows us to understand that multiplication is not restricted to only a certain portion of values. So you can see this with this kind of idea of sliding. As we slide the variables, the output exists for any kind of pair of points x and y. And here, as we would expect, our output will be equal to 6. Let's look at another example. What happens if x is equal to -2 and y is equal to -4? Then the function f will multiply these two inputs, multiply -2 and -4, which means that the blue dot moves upwards, and the output is, as expected, 8. And let's see one final case. If we have x going upwards to 3 and y going downwards to -3, the output will be a negative number, which is -9. Why did I make an example like this? Because by using number lines, we can actually ask, how do derivatives fit into this scenario of finding a derivative of a multivariable function? Okay, what we can do here is the following. First, let's move our x to the value 2 and y to the value of -3 as an example. Of course, the output will be -6. So what we can do now is we can add infinitesimal to the variable x. When we do that, we create what is called dx. And for this change introduced by dx, the output changes for some value which is equal to df. Yeah? But what else can we do? We can also add infinitesimal to the variable y. So this will be equal to dy. And this dy will then cause the output to change for also an infinitesimal value equal to df, which is the blue value. So the interesting thing is that changing both dx and dy, in this case, change the df in a certain way. Let's investigate this a little bit closer. So what I will do here is I will show you both of these operations on the same slide. So on the left side, I will increase x for dx, and on the right side, I will decrease y for dy. And let's see what happens. Adding infinitesimals to both x and y causes the output to change for some amount df. But this amount is not the same. In the first case, as we increase x, which is a positive number, the derivative of the output goes towards -8. And if we increase y for the infinitesimal dy, the output of the function f changes in another direction. So they change in opposite directions because x is a positive number and y is a negative number. Okay, that is interesting. So the question is, what are the derivatives here? And I hope you can see it that there are only two possibilities that we can investigate here. We can investigate what is the derivative of the output f in terms of x and what is the derivative of the output f in terms of y. So there is nothing else that we can do. And then we could call this derivative of the output in terms of x df over dx, and we can call the other one df over dy, but using this notation could be problematic. Why? Because this function actually has 2 inputs, or it can have 100 inputs. We want to differentiate these functions which have multiple inputs and their derivatives from the functions which have only one input and their derivatives. Therefore, there needs to be a notational change in this case. So instead of using d, we will use the Greek letter delta. So we will say that df over dx is now delta f over delta x, and df over dy is now delta f over delta y. Okay? And if you want to be really precise, then we want to also say what kind of inputs are there. So instead of saying delta f, we can say delta f of x comma y. So what we have now is delta f of 2 inputs x and y over dx, and delta f of 2 inputs x and y over dy. And these are the only 2 options we have for our multiplication case. So since now we are considering multivariable functions and their derivatives, we need to use the precise name for the derivatives, which is partial derivatives. So instead of one derivative, we must compute 2 partial derivatives because this function has 2 inputs. And what are these partial derivatives? One is derivative of the output in terms of x and the derivative of the output in terms of the second variable, y. And for you, it might seem that this kind of way of describing derivatives is quite complicated and cumbersome, but it's just a matter of getting used to it. So the most important thing to realize here is that nothing has really changed. In computing the derivative, the procedure is almost the same. So what changes is simply, instead of having one derivative, because we have one input, we now have multiple derivatives called partial derivatives, and each of them is computed in regard to one of the inputs. So if the function has 100 inputs, and if we want to compute the derivative of this function, we will have to compute 100 partial derivatives, the derivative of the output in terms of all of the inputs, independently. The first derivative tells us how changing x influences the output to input ratio, and the second one tells us how changing y influences the output to input ratio. And now, finally, we can answer what is a gradient. So gradient of a function f is nothing really complicated. It is just a vector, or if you do not know what a vector is, we will introduce it later, it's just a list containing all the function's partial derivatives. For example, in our case of multiplication of two numbers, of two inputs x and y, the gradient of this function f will be a vector or a list containing both partial derivatives, one in terms of x and one in terms of y. So nothing spectacular going on there. How do we actually compute the gradient of a function at a certain point? And we will use the same function that we investigated before. So it is f of x and y equals x times y. So let's compute it at the point 2, -3. So x is equal to 2 and y is equal to -3. So now instead of adding the infinitesimal dx to the input x, I will actually add the same infinitesimal, except that I will now call it delta x. And I will now add also the infinitesimal delta y to the value of y on the right. And now this causes our function to change for a certain amount, delta f in both cases. And this amount, as you can see, it's not the same. Therefore, we need to think about two derivatives and see how each of them will change the output of the function. So if we are interested to compute the derivative of the output in terms of x, what do we need to do? So what we need to do is we need to increase x for this delta x, but at the same time we should not change y while we are doing that. And if we do not change y, then y is not actually a variable. So if we cannot change. So what it is if it is not a variable? It's called a constant, which means it's just like any other number. So if we wanted to formalize this, we can say that y is simply equal to -3, because this is where we started investigating the derivatives, at y equals -3. Okay, now that we fixed y, our function f of x and y equals to x times y can be seen as f equals -3 times x, because y is equal to -3. Yeah, we just replaced the value of y by -3. We can use the same formula as last time to compute the derivative. We say delta f over delta x is the limit of this expression, -3 times x plus delta x minus -3x all over delta x, as this delta x approaches 0. So if we'll do some algebra here, we will get new terms, which is -3x, -3 delta x, and +3x. And then -3x and +3x, we can cancel them. And then we have 3 delta x over delta x. And now the question is, can we actually cancel delta x? And the answer is yes, we can. Why can we do it? Because delta x will actually never be equal to 0. It will be a very small number, but never 0. Therefore, as we can cancel 5 with 5, we can cancel delta x with delta x. Then we end up with delta f over delta x equals to -3. So the first partial derivative of the function f of x, y equals x times y at the point 2, -3 is -3. Okay, now let's compute the second derivative, which is derivative of the output in terms of y. So what do we need to do? Analogous to the left side, we need to increase y for delta y, which we already did, but at the same time do not change x, so fix the x. So since x is not changing, it is not a variable. It is just a constant, like any other number. Since we fixed x to the value in which we found it, which is 2, we can simply say x equals 2. If x equals 2, our function becomes f equals 2 times y. Okay? And now we can just try to compute the derivative of this function. We can say delta f over delta x is just the limit of this expression, 2 multiplying in parentheses y plus delta y minus 2y. If we just unscramble this expression, we get limit as delta x approaches 0 of 2y plus 2 delta y minus 2y over delta y. And now we can again cancel 2y and negative 2y, and we end up with 2 delta y over delta y, which we can cancel, and we end up with delta f over delta y is equal to 2. So we calculated values of both derivatives, one in terms of x and one in terms of y, at a special point in time, which is 2 and negative 3.
Let's now try to present a more general case of finding partial derivatives of a function f equals f of x and y equals x times y. So what you should be already comfortable with is that this function has two inputs, thus we have to find two partial derivatives. One is the partial derivative of the output in terms of x, and one is in terms of y. So this is the first partial derivative, delta f of x and y over delta x. And the second one, I'll put it here, delta f of x and y over delta y. So let's start computing them. I will start with the first partial derivative, delta f of x and y over delta x. And this is equal, it's a limit. And I will not use delta x as an infinitesimal. I will introduce a regular variable like h and say, okay, let's see what happens when h approaches 0. And what is the expression here? We have f, but this time, since we are looking at the derivative of the output in terms of x, the x will be the only variable which we will increase for this amount of h. So it will be f of x plus h, comma y, minus the original function, f of x, comma y. And on the other side, we'll have this expression is equal to the limit h approaches 0 of what? Of f x, and then since this time we're leaving the x alone, we are increasing only y, we will write y plus h, and then minus f of x, comma y. Here we will divide with h and here as well. So let's proceed computing the partial derivative of the left side. This is equal to, again, a limit when h approaches 0. So now the question is, what is f of x plus h, comma y? This might seem daunting, but in principle is very easy. So what is our function actually doing? So we have one variable x, and we have one variable y. So whatever the inputs are, x and y, they get multiplied together. So let's bring this to the next step. Here the first input is this one, here the first input is this one, and the second input is this one. Let's also mark it for f of x, comma y. This is the first input, this is the first input, and this is the second input. So we simply need to multiply those inputs. So here we will have x plus h multiplied by y minus x multiplied by y divided by h. So what is this? This is xy plus hy minus xy over h. xy and xy cancel out. And the question is, can we now cancel h's? Well, if they were 0, we would not be able to do it. But the definition of derivative tells us that h can never be 0. It will always be approaching it, but it will never be 0. Therefore, we can cancel them too. So we can conclude that the delta f of x, comma y over delta x, or that the partial derivative of the output f in terms of the input x is equal to what is left, which is y. Let's complete the calculation on the right side. This is equal to limit when h approaches 0 what is f of x comma y plus h? Well, again, we need to simply multiply them. So x times y plus h minus what is f of x comma y? It's just xy over h. What is this equal to? This is xy plus xh minus xy over h. We cancel these two. We cancel h's. Delta f of x comma y over delta y is equal to x.
So now after we calculated it, let's consider how we can represent the gradient of a two-input multiplication. So the function is f of x and y equals x times y. As we can see on the drawing, this function has two inputs and gives us the output f. And we calculated that its partial derivatives are y for the derivative of the output in terms of x, and x for the derivative of the output in terms of y. So we can now write that the gradient of this function is simply gradient of f of x and y is a vector containing y and x. So it kind of flips the input and output. So xy becomes yx. And now let's see from geometric perspective how we can think about finding partial derivatives of multiplication.
There is another perspective. We can look at the function f of x comma y equals x times y, so the multiplication of two numbers, and then the output is equal to capital F. As we discussed before, we can think of any kind of multiplication in terms of an area. So what is the area here? We have two variables, x and y, and we multiply them. Since both x and y are free variables, we can imagine them as kind of being a number line. So this is 0, and now this goes to positive infinity. And we have two of these number lines. And on one we take the value of x, and on the other one we take the value of y. What this gives us is two lengths, or two inputs, input 1 and input 2. So what we can do now is we can construct a rectangle, this side being x and this side being y, and this area here is x times y. What is the derivative here? So let's make two more of these rectangles. So this is xy, xy. Now imagine that we want to find the derivative, and we have two inputs which can both influence the output f. So in the first case, we want to find the partial derivative of the output f in terms of the input x, which means that we need to increase x for a very, very small value and see how does this affect the output. What we can do is we can introduce infinitesimal delta x here and add it to our rectangle. So this is dx, and then this area becomes what? Becomes y times dx. Now let's find the second partial derivative, the derivative of the output in terms of the second variable y. What we do is we introduce another infinitesimal, we'll call it delta y, and add it to the y in the second case. This is delta y, and this is the new area, which is x times delta y. And now to find the derivative, we need to ask the question, what is the ratio of these two areas to the inputs that cause them? On the left side, we have y dx over dx, and on the right side, we have x dy over dy. And if we ask what is this equal to as dx approaches 0 or as dy approaches 0, we will see that the first one is just equal y and the second one is just equal x. So this is a very easy way to understand why do we get the values we get for computing the partial derivatives of a product of two variables x and y.
Now let's look at another very simple case It is a function which has two inputs, x and y, and its output g simply adds these two inputs together. So g is equal to x plus y. Let's try to find its gradient.
So we have a function which is g of x comma y equals x plus y. And then this is also equal to the output g, variable g. Okay, what we are interested to find is the partial derivative of g in terms of delta x and partial derivative of g in terms of delta y. And this is equal to limit as h approaches 0 of what? In the first case, we have g of x plus h comma y minus g of x comma y. On the right side, we have g of x comma y plus h minus g of x comma y, and we divide both sides by h. So what do we have here? Here our inputs are x and y, and then we simply add them. So we add the first input and the second input, we add the first input and the second input. On the other side, we also add the first input to the second input, we add first input to the second input. So we simply add these things. So on the left side, we will have x plus h plus y minus x plus y. On the right side, we also have x plus y plus h minus x plus y. Both sides divided by h. Here we'll have h and negative h cancelling out, y and negative y cancelling out, and the same will happen on the other side. And we will also have h's cancelling out, because they are two numbers not equal to 0, and we will conclude that both partial derivatives are simply equal to 1. So delta g equals to 1, and delta g in terms of y also equals to 1.
As you can see on the left, for the function g of x and y, which simply adds two inputs, x and y, we have a representation which shows us both gradients. As you can see, this is just a vector of two ones. So now we come to a very nice part. We already analyzed these three equations, and what can I tell you about this is that by knowing these three functions, you're able to construct many machine learning models, especially neural networks models. The only thing that we need to know in this case is what are the derivatives of these functions. And we already know the derivative of the sigmoid function is the output of the function times 1 minus the output of this function. Derivative of the two input addition is simply 1 in both cases. And the derivative of the multiplication function in terms of x is y, and in terms of y is x. So by knowing these three things, it is very easy to construct neural network models.
As an exercise, let's try to think what kind of partial derivatives we need to compute in this case. So what we know is that we have three inputs, x, y, and z, and we have only one output, which is this f. All the values in between serve both purposes. For example, g is also the output of one of these functions and also the input for the next one. So what do we need to find? We need to find three partial derivatives. What are they? The first one is delta f over delta x, second one is delta f over delta y, and the third one is delta f over delta z. So how to start thinking about this? So we need to have delta f over delta x. There are multiple steps in between, so this derivative is not so straightforward to find. But what we can do is we can use the chain rule. Instead of computing this one long line, we can simply erase it and say that delta f over delta x is equal delta f over delta g times delta g over delta x. Let's write that down. So delta f over delta x equals delta f over delta g times delta g over delta x. And as you can see, we can always cancel delta g's, so these middle steps. But we do not want to do this. In the same way, we can also say that the partial derivative delta f over delta y can be decomposed into simpler derivatives. So let's erase it. We can write it as delta f over delta g times delta g over delta y. So delta f over delta g times delta g over delta y. So as you can see, we used chain rule to simplify this expression. What happens with delta f over delta z? Well, as you can see, there are actually no steps in between there, because z and f are connected by means of a single function of multiplication. So let's compute delta f over delta z first. If you can just pretend that this side does not exist, you can see that what we have here is multiplication, and we have two inputs. First input is g, and the second is z. And we are asking what's the partial derivative of f in terms of z, and as we know, if we have multiplication, the partial derivatives are kind of the opposite values. So if we have x and y as inputs, the partial derivatives will be y and x, so the other one. So the partial derivative of f in terms of z will be the other one, which is g. So this is equal to g. The question is, what is g equal to? So as you can see, g is the output of addition. So g is equal to x plus y. Equals to x plus y. Then let's do this one, delta f over delta g. So delta f over delta g is the same situation like we just had with z. It's just that delta f over delta g will be the other one, which will be the z in this case. So this will be equal to simply z. And what is delta g over delta x? As we said, if we have addition of two numbers, their partial derivatives are all equal to 1. So this is just going to be multiplied by 1. Okay, let's do delta f over delta g. Again, delta f over delta g will be the same as in previous case. Simply is going to be equal to z. And in the same way, delta g over delta y, because it's just addition, will be equal to 1. So we can multiply them. So now let's say this whole function, which has 3 inputs and 1 input, we will call it p of x, y, z. And let's then describe the result or the gradient of this function, p of x, y, and z. And its gradient is just z, and x plus y. So that's it. The last coding exercise we will be doing today is about minimizing or maximizing multivariable functions such as f of x equals x times y. So the first task is to implement exactly this function, and we can do it like this. So def, the function will be called f, and it will now have two inputs, x and y. Let's do it with capital letters, although this is not necessary. And this function will simply return x times y. So very simple. Now it says evaluate the function f for various values of x and y. So f of 3, 5 is going to be 3 times 5 equals 15. F of 6, 5 will be 6 times 5 is equal to 30. So nothing unexpected here, nothing remarkable. The task is to implement the Python function f partials that returns both partial derivatives of the function f of x and y. So we can define this function as f partials. It takes inputs x and y just like the function f, but now we know what the partial derivatives are. We computed them beforehand. So the partials are just kind of the opposite values of the inputs. So if the inputs are x and y, then this function should return y, x. Now it says evaluate the Python function f partials for various values of x and y. So f partials of 5 and 3 should just be the same values but presented the other way around. So f partials of 5, 3 should be 3 and 5. F partials of 3 and 5 should be the opposite values, 5 and 3. All right. Now the task is to assign the output of this function f partials to a variable current partials and print its output. All right. Why are we doing this? So if I say current partials equals, let's copy this and paste it here, f partials of 3 and 5, we know that the f partials will return 5, 3, and this will be stored in this variable current partials. Let me show you that. So if I type current partials, you'll see that it will return 5 and 3. Why did I do this? Is just to show you how we can isolate the first partial or the second partial by using indexing in Python. So it asks us, get the partial derivative in terms of x from the variable current partials. So we can say current partials, copy and paste. And if we use the square brackets, if we use the value 0, in computer science we start counting from 0. So 0 will actually return us the first value of this list, 5 and 3. So it will return us 5. If we want to take the second partial derivative, we should just say current partials 1. 1 will give us the second value. Again, we start to count from 0, so 1 is actually the second element. So the second element of this list is 3. So we got, by typing this command, we got the first number. By typing this command, we got the second number. If we had more values, we'll simply use the appropriate index -1. So if we wanted the 100th element, we will use the index 99. Okay, the exercise now asks us if we are at the point x old is 2 and y old is -3, and we wish to minimize our function f of x, y, write code that computes new values of x and y, x new and y new, which if taken as inputs to this function f of x and y, will decrease it. All right. So first we type x old equals 2, and then we can just type it on the next line, y old equals -3. Fine. So we wish to minimize our function. How do we do it? Well, now we have two partial derivatives, which means we need to minimize both of them. Let's just compute the partials first. So we will say current partials equals f partials, which computes the partial derivatives of this function, and the values are x old and y old. All right. So now if we want to compute x new, we need to do it separately from y new. So x new is equal to x old. Since we want to minimize our function, we will use the minus sign. So minus current partials 0, because 0 will give us the first partial, times some small value, 0.01. And then we can also, below it, compute y new equals y old minus current partials of 1, which is the second value, times 0.01. All right. These are the old values, x and y, which are the inputs. Let's see what are the new values which should minimize the function. So x new will be 2.03, so it's larger than x old, and y new should be -3.02, so it's actually smaller than the y old. And now the task is to compute the output of f of x and y for the variables x new and y new. But first, let's evaluate the function f for the values x old and y old. So as expected, 2 times -3 is equal to -6. So this is the output of the function f for the old values of x and y. But if we say f of x new and y new, we will get that the output of the function for the new values of x and y is actually smaller than -6. It is -6.13. So we succeeded to minimize our function f of x and y.
Okay, this will be all for this class. I hope that you enjoyed it. And next time, we will actually use this knowledge that we learned today to derive some basic machine learning models, and we will start with one historically very important model called the perceptron model. Thank you, and see you next week.